Farmers have been struggling with germination and nutrition of the seeds that they plant, as the dispersal of seeds affects the nutrition they receive and how they grow. Specifically, statistics show that farmers in Karnataka, India, reportedly saw that around 50% of maize seeds that they sowed failed to sprout, according to the Times of India. Researching more about the seed dispersal in various seeds, we found that the physics behind orange jewelweed allows it to disperse in an explosive way, and making the seeds airborne will allow nature to take its course in seed dispersal. Using the design of the orange jewelweed, we decided to make a this inspired launcher.
Now, we will drive the range of a spring-powered projectile. Hooke's law tells us that the spring force is equal to the effective spring constant times the compression distance. So to find the work done due to the spring, which is the potential energy of the spring, we can simply integrate this function, and we get our potential energy of the spring as half k effective times x squared. Our spring potential energy converts to kinetic energy, so setting half k effective x squared equals half mv squared, we can derive a formula for the launch velocity of our capsule. Using the horizontal and vertical components of velocity, we are able to derive what they are in terms of the effective spring constant, mass, and the compression distance, and the launch angle, which is theta. Using the vertical equation of motion, we can derive the time it takes for our projectile, in this case, which is our capsule, over the whole flight. And then we can plug in our value for Vy. We know that the range is always the vertical component of velocity times the horizontal component of velocity times the time. So we can simply plug this in to get a formula for the range. We want to optimize the range. So to do this, we can set the derivative. We can find the optimal angle by setting the derivative of range with respect to theta equals 0. We solve cosine 2 theta equals 0, 2 theta equals 90 degrees, and we get theta equals 45 degrees. So hence, we get our equation of motion for range as k effective over mg times x squared. And here's a demonstration of how we expect our projectile to work.
This is our wheel, designed to give our design mechanical advantage. Initially, the wheel was falling off and we couldn't fix it to the board in a manner where it couldn't fall. The problem was that the wheel was providing a lot of torque upon the rod, causing it to fall. To address this problem, we used a box full of rocks and placed the rod with the wheel inside this box to counteract the torque provided by the wheel. We later used this technique to counteract the legs problem.
For the spring mechanism, this was the first iteration of the spring pancake. We drilled 2 holes in a steel disc for the rope to thread through and glued 7 springs to the periphery. However, this mechanism presented some issues, particularly due to the asymmetric drilling of the holes, excessive stiffness and short length of the spring, as well as the heavy steel disc which would have absorbed energy that should have been used for launching, all of which would have contributed to a dysfunctional launcher. Afterwards, we replaced the springs with longer ones and the steel discs with PVC. The new discs were lighter, which allowed for the ball to be launched farther as the disc would move more easily. But the main problem with this design was the fact that the helical springs, unrestricted, would rotate too easily and entangle with one another, reducing the compression.
To restrict the springs from rotating, we decided to place them around steel bolts. We drilled 4 holes for the springs and secured 4 bolts with the nuts. This allowed for the spring to compress completely without rotating with one another. We also drilled full 4 holes to the upper disc and used nuts on the top to secure the disc from falling off. This allowed the disc system to snap back fully due to the springs being able to fully compress.
Here is a video of our product launching after complete design. This is the box of seed capsules for easy access of use for our users.
These are our position versus time graphs. As you can see in the y versus time graph, the capsule experiences constant acceleration due to gravity and other forces.
Yeah, I'm recording.
This is a video where we attach the mass to the spring to test for damping. As you can see in the graph, the spring and the mass are under damping.
Go.